Every molded part has a hidden number attached to it. It's usually 2 to 4 millimeters. It gets set early in the design process, written down exactly once, and almost nobody argues about it. Yet from that moment on, this tiny dimension quietly dictates the entire production reality. It governs tooling cost, factory floor cycle time, and final surface quality. Long before a design is even finished, this single, seemingly minor manufacturing parameter has already decided what the object is allowed to look like. The intuition almost everyone brings to that dimension is simple. Making a wall thicker will make it stronger. This diagram shows the reality of a thick plastic wall cooling in injection molding. The outside of the section solidifies first, but the inside keeps shrinking. The result is either a visible sink mark on the outer face or a hidden void directly in the middle of the part. The time penalty here is severe. Cycle time scales roughly with the square of wall thickness, meaning a designer who quietly adds a single millimeter for structural confidence can double the time each part sits in the tool waiting to cool. In composite materials, this exact same instinct produces resin-rich zones. The excess mass creates a pool of the weakest material in the laminate, exactly where someone was trying to add strength. Adding mass burdens the manufacturer with extra weight and slower production cycles without actually solving the structural problem. Stiffness in bending is a product of section, how material is arranged in space, rather than total mass. Look at this graph showing the neutral axis. As you move material away from it, stiffness rises exponentially by the cube of the depth. Contrast that with making the wall fatter. Stiffness increases at a 1-to-1 ratio, carrying a full weight penalty. The entire craft of thin wall design is extracting maximum structural stiffness from zero-cost geometric features, like ribs, gussets, and folded edges. The canonical demonstration of this physical principle is over 60 years old. This is the Panton chair, the world's first molded single-material plastic chair. It functions as a cantilever that holds a fully grown adult without the need for back legs. It achieves this because Werner Panton's sweeping S-curve provides the necessary structural section. Because the visual shape and the physical strength were the exact same decision, the chair took several years and multiple material generations to actually manufacture. When an object's aesthetic shape aligns this perfectly with its structural section, wall thickness functions as the product's core architecture. Today, 3 distinct external forces are pulling on wall thickness from directions that have absolutely nothing to do with basic load bearing. The first is disassembly. As automotive sustainability goals push for higher end-of-life material recovery, designers are forbidden from bonding stacks of dissimilar materials together. A mono-material approach forces you to find your stiffness purely in the section geometry. The second pressure is the disappearance of the tool. Large-format additive manufacturing removes the mold entirely, allowing thickness to vary continuously exactly where the load demands it, rather than remaining uniform for the sake of the factory. The third is regulation. Overhauls in modern safety protocols introduce entirely new post-crash load cases, like high-voltage isolation, which must eventually be absorbed by the object's physical section. The combined demands of sustainability, printing technology, and safety laws are systematically eliminating the luxury of uniform, unconsidered mass. Wall thickness is traditionally treated as a manufacturing parameter, handed over to engineers only after the aesthetic surfaces are signed off. This is actually the point of fusion where aesthetic shape and physical structure become a single, inseparable decision. This critical decision happens silently, usually by default, at the very beginning of the concept phase, long before anyone has actually drawn the thing it will end up governing. Design decisions are cheap as a sketch, brutal once tooled. See every angle before you build. Ensure your early concept decisions survive the reality of the tooling process by exploring generative consistency with Depix design intelligence.